Welcome to Study Loop.
In this problem, we are given nitrogen gas, which is expanding in a container, but its temperature is going from the initial temperature of the 50 degrees Celsius to the temperature of 10 degrees Celsius. And at all times, the pressure is constant at the given value of 3.10 to the fifth pascals. So for the part A of the solution, we need to derive and evaluate the number of moles of the gas. Since we know the amount of heat that is getting liberated from the gas system, we can derive the number of moles, which is given here, from this formula of heat. So this will imply that number of moles equals heat divided with Cp times delta T. We know the change in temperature and we know the heat capacity. So we can just substitute the known values. N equals, this is going to be minus 2.50 times 10 to the fourth joules, and this is going to be 29.07 joules per mole Kelvin. And then the difference. The difference will be, we will transform the given values of the temperature into kelvins, from Celsius to kelvins. So this will be 283 kelvins minus 323 kelvins. When we put these values into a calculator, we obtain that N equals 21.5 moles. This is for the part A of the problem. Next, for the part B of the problem, we need to actually evaluate the internal energy of the system when the pressure is constant. So here we will still use the heat capacity for the constant volume. And this is because when we evaluate the internal energy of the system, we always use the heat capacity for the constant volume when it comes to gases. So delta U equals NCV delta T. Then substituting the known values, this is going to be 21.5 moles times 20.76 joules per mole Kelvin times the difference of temperatures, and when we put these values into a calculator, we obtain that the internal energy change is negative and it is minus 17.9 kilojoules. For the part C of this problem, we need to find the work done, and this will be derived from the first law of thermodynamics. So it will be Q equals delta U plus the work done. Therefore, this implies that the work done is equal to Q minus delta U. We already evaluated Q and evaluated delta U, so we can directly substitute and evaluate for the work done. So the work done is going to be minus 2.5 times 10 to the fourth joules minus, and then the negative value, 17.9 times 10 to the third power joules. And when we put these values into a calculator, we obtain that the work done is minus 7.1 kilojoules. So this is for the part C of the problem. And for the next part, and this is the last part of the problem, this is the part D, we actually need to find the heat liberated at the constant pressure. So again, from the first law of thermodynamics, but in this case, we have to consider that it is done under constant pressure. So and also at a constant volume. It is going to be both constant pressure and constant volume. So the only change that can happen here is basically the change in internal energy. So no external work will be done by the gas or on the gas. Therefore, the first law of thermodynamics and its value will change. The quantity of Q will change, since W plus delta U, here W will be equal to 0, since no volume is changing, no expansion or compression. So, and the value of delta U is the value we already know, we already evaluated it. So we can just substitute immediately that from the previous examples, from the part B of this problem, Q equals, in this case, negative 17.9 kilojoules. So obviously the heat which is liberated at a constant volume is less than at a constant pressure, since in this part of the problem, part D, we are also taking into account that the volume is not changing, while in the previous or in the beginning we are given the liberated heat when the volume changes, and this heat is much larger than the heat we obtained right here, which is the conclusion of the problem. So here